about transmission line. Last time we started to speak about special cases of the lossless transmission line. So our focus is lossless transmission line. Lossless transmission line means the conductor has infinite conductivity and the dielectric between the two conductors has zero conductivity. This is the meaning of lossless transmission line. Last time we covered the short circuit transmission line. Today we are going to cover the remaining topics about the open circuit transmission line, application of short open circuit transmission line, and some other cases. If you remember last time, we assumed that if we have a load that is short circuit means ZL equal to 0. In this case, what is input impedance? If you have ZL equal to 0 here, what is input impedance? How's the name?
Yes.
انت.
خالد.
خالد لو ZL equal to 0, what is it input? If ZL equal to 0 يا خالد. You read the question. ZL equal to 0, what is it input? Just put ZL equal to 0.
Okay.
What is it input? The input impedance of the transmission line. Wrong. خالد ZL equal to 0. This 0 and this 0. What is left in the equation? J Z0 10 bit L. So right here. So the input impedance here very simple from this equation as Khalid helped us is JZ0 10 bit L. What does this mean? What does this equation mean to us here? The input impedance is reactance, right? Has no real part. This reminds us of the case of inductive load or capacitive load. So basically, JZ 10 beta L can be inductive load, يعني if the 10 beta L is load positive value. This will lead to the case as if you have inductance. يعني looking here, this is the voltage and the current. Short circuit transmission line means gamma is -1. The reflection coefficient, which is here, the reflection coefficient will be -1, and the standard wave ratio is infinity. This is the case of full reflection. So all the signal is being reflected back. If you take gamma equal to -1 here in these two equations, this will give you V and I at any point along the transmission line. If you divide V by I, this will give you the input impedance, which I can just say. This input impedance of the transmission line when D equal to L. Because D equal to L means you are at the load. If you remember, D equal to 0 is the location of the generator, D equal to 0, and then D increases until we reach to the generator when D equal to L. If you take the voltage at any point along the transmission line versus D, this will give you cosine function, or give you sine function. Now look at the voltage here. This is the voltage V of D, I of D, at any point on the transmission line, assuming the load is short circuit. If the load is short circuit, any point here will have this V and I. If you take V and I at the generator, this means D will be equal to L. So the voltage is sine wave and the current is cosine wave. Looking here at the variation of the voltage and the current, does this make sense? Yeah, does this behavior of the voltage on the short circuit transmission line, does it make sense for you? The voltage and the current, this curve?
Yes.
Why? Why I think?
Because
This is his. Huh?
Because when the voltage is maximum, the current is zero.
Yeah, this is good. What else? We have short circuit here. So this means the voltage must be zero at the load, and the current will be maximum. Short circuit means the current is maximum. Later, now we will take open circuit case. In the open circuit, you will have some voltage, maximum voltage, and zero current because it's open circuit. So it makes sense to agree with the structure of the line. What about the impedance? What about the input impedance? The impedance here. We're interested in the input impedance because we can get rid of the whole thing and we can remove the transmission line and the load and just use the input impedance with the generator. The input impedance is JZ0 10 beta L. If you take the tan function and draw the tan, how does it look like? This is a tan beta L function. I take the input impedance versus D. As you can see, this is a tangent function. Sometimes it is positive based on the distance. D from 0 to 1/4, it will have a positive value. This means the transmission line will have positive reactance, which is similar to inductance load, as if the whole thing is acting like a simple inductance. If the tan beta L is negative on the, if you go further along the distance of the transmission line, or if you have bigger length, this is the distance d, this is the distance d. So if the length of the transmission line between lambda over 4 and lambda over 2, you will have negative reactance, which is impedance of capacitance. So as you can see, the impedance of this transmission line, the input impedance, change between positive and negative. Positive means inductance, negative means capacitance, as you know from high school. Also, at certain distance, the impedance will reach, when d, the distance equal to lambda over 4. What is the impedance, the input impedance? What's the input impedance here? Infinity. The 10 by over 2, this is like 10 by over 2. 10 90 degrees infinity. The next one is 10 3 by over 2. So at some places along the line, based on the line, you have short circuit here. Based on the location on the line, you will have either inductive load as the input impedance, capacitive load, or open circuit. Open circuit because the impedance will go to infinity. So by the proper choice, by the good choice of the size of the transmission line, you can have different behavior of the impedance. It can be inductance, capacitance, or open circuit. So as we said last time, that this guy, the short circuit transmission line, can act as inductance, and in this case, the input impedance of this transmission line will be the same as you have inductance, which is j omega n. So you can find the equivalent L from this equation. Also, you can find the length of the transmission line that can give you inductance load. You can find the good size of the transmission line that can replace the whole thing by inductance. On the other side, the whole transmission line can act as capacitance, and in this case, we can use the input impedance of the transmission line, which JZ. What was the input impedance we just mentioned? The input impedance of short circuit transmission line equal to J Z0 tan beta. So based on the sign of this tan, you can have either inductance or capacitance based on this guy. Because this is positive also. And this can be positive or negative. If it is positive, it will be like inductance. If it is negative, it will be capacitance. Yes,
and this customization can be done within only half lambda, is that right?
Within half lambda, because if you look here, up to lambda over 4, the tangent will have positive sign, so it can be inductance. From lambda over 4 to lambda over 2, you can have capacitance. But you can have bigger transmission line. You can have longer transmission. You can go further on this axis.
Yeah, but it will not add anything.
To alternate, to repeat the same behavior. So based on the size, you can have inductance or capacitance. But up to lambda over 2, as you said, and he's saying up to lambda over 2, you can have both cases. Which is correct. This is what we mean. Why this is important to us? Why it is important to replace the transmission line with inductance or capacitance? How is this interesting?
We can use it for different applications.
Like what? In integrated circuits, it's very difficult to design actual inductance and capacitance at high frequency. Okay, not easy. But the much easier is to have a two piece of braided lines shorted. This will act as inductance or capacitance without the need to have actual inductance or actual capacitance. More expensive to have this actual element, and not easy even on integrated circuit level. Okay, yes.
At what frequency do we switch from physical inductors to line inductors or PCB inductors?
Between line inductance?
At what frequency do we switch from the components to the line inductors?
Yeah, I'm not very sure about what frequency, but I would expect above 1 megahertz. It's very difficult to have actual inductance and capacitance. But I guess yes, I guess so. We covered this problem last time. Please try to solve this problem to the very end. Sometimes it is getting tricky in the middle, okay? And you don't notice this until you solve it yourself. If you read it quickly, you'll think it's easy. But if you have the solution to write it yourself, you'll see it has some tricky point in the middle, okay? So you can You better solve it yourself from the beginning. It needs some time, it will take time. You have to spend time. Then look at the situation if you are stuck, then try to solve it yourself from your head. Okay? Now we move to the other case, which is the open circuit. So instead of short circuit, we have open circuit. So if the transmission is open circuit, the load is infinity, gamma at the load, what is gamma here? What is the differential of gamma, ya shabab? The reflection coefficient at the load. What is the reflection coefficient here?
Zero minus one.
The equation, what's the equation?
ZL minus zero.
ZL minus Z naught over ZL plus Z naught, right?
Yes.
So in case ZL is infinity, what is gamma?
1.
1, right? It was minus 1 in the short circuit. Now it's 1. What's the meaning of 1 as a reflection coefficient? Everything is traveling to the load will come back, will go back. The load is not going to absorb any energy. There is no energy transferred to the load. Everything is coming back for reflection with phase 0. And even the incident wave and the reflected wave will be in phase because gamma is the ratio between the reflected to the incident wave. The standing wave ratio, what is the definition of S? Standing wave ratio. 1 plus magnitude of gamma over 1 minus magnitude of gamma. So if gamma is 1, this will be in phase. This is the worst case. The worst case is the standing wave ratio is 1. That is infinity, sorry. Everything is reflected back. So based on this, what is the input impedance of this transmission line? And if you are here, looking this way, what is the impedance at this point?
Infinity.
Do you know, Ali? What is the input impedance?
In between.
In the question now, ZL equal to infinity. What's the impedance?
It will be infinity.
Huh? ZL is infinity, open circuit. So what ZL equal to infinity here? What will be the impedance? Yeah. What's the impedance? ZL is infinity. Question now.
Z0 over imaginary part.
Okay, and what ZL equal to infinity is this equation? The input impedance. What will be the input impedance? شايف ZL is infinity. عوض بقى في المعادلة. What's the input impedance? But the state is very just checking with you. How is it infinity في equation ده?
0
Not 0. Divide by infinity طبعا نعم. Numerator and denominator.
You have to differentiate.
You don't need to differentiate. No, it will not be like this. Just divide by over ZA. Divide the numerator and denominator by ZA. Okay. Who knows what is infinity means? What ZA is infinity. Raise your hand if you know. مصيبة. مصيبة. The equation is there. Just put ZL equal to infinity. It will be infinity over infinity. Then divide the numerator by ZL. So it will be not Z0. Not why Just do it by hand. Write it down. And this equation, put the ZL equal to infinity. You need to divide by ZL from on the bottom. I'm sure if I bring grade 7, 10 plus 2.
Z naught over J tan B tan.
Exactly, which is you will divide by ZL. So if you divide by ZL, this term will disappear. And this term will disappear. You will have this one. So minus J will be minus J, Z0 cotan. 1 over 10 is cotan, right? Yes. So this is what it means. Then what it means is minus J, Z0 cotan beta A. This is the voltage, and also you can use the equation of input impedance and substitute here to find the input impedance, as I did, or use V and R. You have V and R. What's going to change this two equation? What is new? What should I add and include here? Gamma equal to 1. Put gamma equal to 1 in this equation, because gamma is 1 here. And D equal to L, because this is input impedance. D is 0 at the load, L at the generator. So both D equal to L, then divide B over I, this will give you the same equation here. So the input impedance of the open circuit transmission line is cotan. What does this mean? يعني compare this equation by the open circuit. This was the short circuit equation. What is the difference between them?
It is the inverse.
So this is input impedance of open circuit transmission line minus J Z0 tan becomes cotan beta L. Cotan means 1 over 10 like this. Right?
Yes.
So what does this mean? Look at this equation.
The inverse of the.
So if beta L here is some angles that makes the tangent positive, this means negative input impedance will imply positive if the input impedance of short circuit is positive. The same transmission line, if ended in open circuit, will be negative input impedance. Are you getting this? And you have a certain transmission line. If you make it short circuit, it will give you positive input impedance. In this case, the open circuit case of the same transmission line, make it open circuit, it will be negative input impedance. Okay? So you can switch between positive and the input, positive and the negative input impedance if you change the node. Same transmission line, same beta A. Okay? What does this mean? This is the voltage. The voltage here is cosine. Remember, in the short circuit case, the voltage was sine and the current was cosine. Now we have the other case. The voltage is cosine with current sine. Why? When we have this switch, in the previous case, for short circuit, the voltage sine with current cosine. Now we switch this. What does this mean? Does this make sense? Yes, open circuit, so the voltage will be maximum. And the current will be 0. So cosine and the sine. Makes sense. For the input impedance, look at this input impedance. Do you remember the case of the short circuit? This guy?
Yes.
It was the other way. It was positive, negative, positive, negative. So the two guys must have two opposite sides. Yeah, same transmission line. If you make it short and you have positive input impedance, if you make it open, you will have negative input impedance. So you can switch between negative and positive if you switch the node, because the equation is the same. Yani tan will have the same sign as cotan. If this guy is positive, this guy must be positive as well. So what is going to differentiate the two guys is these two sides. Are you getting this? Any question, Shabab? We have quiz today, I guess, right? Let's come to the quiz today, 5:15. Now we move to some application. Say we have, I give you the input impedance of the short circuit transmission line and the open circuit input impedance, same transmission line. One case was short circuit load, another case was open circuit. And I give you the two input impedance. Okay, these two guys I give you. How can you use these two equations to find Z0, for example? Can I find Z0 from these two equations?
Yes.
The characteristic impedance. Yani you have some line and I don't know it's a characteristic impedance. But I know the input impedance in case it is short or open. I have these two equations. Can I use them to find what is Z0 here? What is Z0 from these two equations?
Zn over.
You will divide the two guys, right? To multiply. You can divide them. If you divide them, it will be this equation. Alright? You will multiply them, sorry. If you multiply 10 times cotan will be 1. Right? And minus j will be 1. So, and then you have to take the positive sign of the square root. Square root could be positive or negative, right? But Z0 must be positive, so you will take the positive sign. So if you have these two guys, you can simply characterize the transmission line. You can know its name, it's a characteristic impedance. And this is what we have a device called vector network analyzer. The vector network analyzer is a device that can give you the characteristic impedance of the line. How does the device work? It measures the input impedance in case of short and open, and then it does this math to give you the input impedance. What else I can get from this two equation? In addition to Z0, what else I can get? The length of the line. I can get beta L. Beta is 2 pi over lambda. I can get L, the length of the line. How can I get beta L from this equation? This is the device. So tan beta L, if you divide the two equations, it will be negative square root of negative Z input short over Z input open. Very easy. Take this over this and remove the negative sign. Take square root. This will give you tan beta L. So from these two pieces of information, I can find another two pieces of information. If I give you these two guys, you can easily characterize the line. Find the characteristic impedance and find the length. Does this make sense? Huh? Is there a mistake?
Find the length, Doctor.
The length is from here.
We will find beta multiplied by
Find beta is the frequency 2 pi over lambda. So if you know the frequency, should know the frequency. So you can find beta 2 pi over lambda and then find L from this equation. But did I make a mistake? What is the meaning of this negative here? Under the square root.
Imaginary.
Remember, this guy will cancel G. Yeah, G will be cancelled eventually. So, would we have 10 bit L as the imaginary part as G? Huh? So, what's the meaning of this negative? And the ratio here, the ratio negative ZM over ZM, eventually will be positive or negative? Why positive?
See, honestly.
Because if you remember the behavior of the tan and the cotan, they will never be the same sign. If the tan, if this guy is positive, that the emotive impedance, the short circuit is open circuit. This curve is this emotive impedance, short circuit. The other guy is open circuit. So one of them is positive, the other must be negative. Okay? So the negative will cancel the negative. And one of them will be positive, the other must be negative. The other negative will cancel this negative. So end up by positive value under the root. Okay? So this is a good example. I want you to read this example and solve it by your heart. Okay? It tells you, it gives you the emotive impedance. It's very straightforward. It has a little, it gives you the emotive impedance of short circuit case, emotive impedance of open circuit. So it gives you these two values. ZM with short and open. And it asks you to find the characteristic impedance and the beta, and they give you L. So we'll use the same two equations, Z0 and 10 beta L. But they give you information here that the transmission line is between 3 and 3.25 lambda. The transmission line is between 3 and 3.25 lambda. So your answer should be within this range. When you find the beta, you must consider this range. So the information given here is that L must be between these two guys. This means beta L will be within what range? Yeah, I know L. Can I know the range of beta L? It is 2 pi over lambda, right? You will just take, you have beta L. Beta is 2 pi over lambda. Okay, L can be this guy or this guy. So use the two values of L. This will give you the limits of beta L. So when you solve for the 10, when you go, remember, from the given information, L has certain limits. So beta L will have some limits from 6 pi to 6.5 pi. In which quadrant do we have beta L? First, second, third, fourth quadrant. Low 0 pi over 2 pi, you know the quadrant? أي ربع.
First.
The first quadrant. Well, 6 pi is 0, right?
Yes.
6 pi, 2 pi, 2 pi, 2 pi, you will come to 0. And 6.5 is like pi over 2. Agree? This is pi over 2, so it's between 0 and pi over 2. This is the first quadrant. So when you find that, when you solve for 10 beta L, it must be in the first quadrant plus 6 pi. Yani when you solve for this equation, it most likely it will give you an angle between 0 and pi over 2. To stick with this limits, you must add 6 pi. And what I'm saying is, when you solve for the emotive impedance, the characteristic impedance is square root Z emote, short Z emote, very easy, square root. For the 10 beta L, it will give you this answer, square root 1 over 3. What is beta L here? What's beta L when 10 is root 1 over 3? What is beta L? Sine over cosine. Sine over cosine. 10 is sine over cosine, right? What is sine over cosine that give you root 1 over 3? So it's either 30 degree or 60 degree.
Yes.
Which one? 30 degree, right? Sine over cosine will give you this guy. So beta L by 30 degrees. What is 30 degree? By over 6. Does this agree with the given limits? The given limits saying that
Yes.
beta L is between 6 pi
Yes.
and 6.5 bar.
Yes.
So the 30 degree must be added to 6 bar to have detail in this range. Okay? When you add 6 bar, you add nothing. 6 bar means 0, right? 2 by 2 by 2 bar. So whatever angle you will get here, if it is not within this range, you need to add 2 by 2 by until you reach to the given range. Does this make sense? So please read this example again. As I told you, this is like, yeah, in some example you will find some tricky point like this. You need to practice. Now, we have a special case if the length of the line is n lambda over 2. 1, 2, 3 lambda over 2. In this case, what is the M impedance? What is the M impedance? When the length of the line is multiple number, integer number of lambda over 2. Half wavelength, we call it half wavelength, lambda over 2. What is the M impedance? What's tan beta L? You have tan beta L. Beta is 2 pi over lambda. L will be something like this, n lambda over 2. If you take the tan, it will give you 0. Agree? In case the length is n integer times lambda over 2. So if the tan is 0, so tan is 0, tan is 0. What is the impedance? ZL. No change. So if you have a transmission line of any Z load, any load here. If you move lambda over 2 from the line here and find the impedance, what is the impedance? ZL, same as the transmission doesn't exist. So the impedance is repeated every lambda over 2. If you move another lambda over 2, so you are 1 lambda away from the load, the impedance is ZL, no change. Okay, in between you have different impedance, of course, but I'm saying if the line is integer lambda over 2, 1, 2, 3, whatever lambda over 2, no change. Okay? This is useful in some applications. So the limit impedance is the same as the load if the line has a length of n lambda over 2. N is integer, 1, 2, 3, whatever. What about if the length of the line is lambda over 4? Yeah, if it is lambda over 2, ZL will come here. What about if the line is lambda over 4? Again, go with the equation, same equation. No? Every time we come here. If the length is lambda over 4 here, what's tan beta L? Beta is 2 pi over lambda. N is lambda over 4. What is tan beta L? 2 pi over lambda, beta, 2 pi over lambda. N, lambda over 4. What is beta L? What's your name? What's your name? What's beta L use? يعني beta is 2 pi over lambda. L is lambda over 4. What is beta L? Pi over 2. So 10 pi over 2 is? What's 10 pi over 2, Muhammad? Sine over cosine 1 over 0. Infinity. So we can divide by infinity. What will be Zm? The tan, if it is lambda over 4, the tan is infinity. So this guys will disappear, right?
Yes.
So what is going to be this now?
0.
Sid nuts.
If this is Z0 square over Zm, right?
Yes.
This guy is infinity. So this and this will disappear and remove these two guys. So it will be Z0 over Zm. In case the line is lambda over 4. So if the line is lambda over 4, whatever ZL here, the input impedance will be, and if you look here at this side, if you argue, what is input impedance? Z0, whatever Z0 square over lambda over 4. Sorry, over ZL. Z0 over ZL. Very easy. Z0 over Z0 square over ZL. In case the line is lambda over 4. Okay? Or 2 lambda over 4. If we go another lambda over 4, would we have the same answer?
No, we'll have ZL here.
Yeah, this lambda over 4. Take another lambda over 4. So you are at lambda over 2 away from the load. What's the impedance? ZL is the case we have taken. So it's lambda over 4 or 3 lambda over 4. You have to move another lambda over 2. So this case is repeated because the tan will give you infinity at pi over 2, 3 pi over 2, 5 pi over 2, right? So at each odd number times lambda over 4, and 1, 3, 5 lambda over 4, the impedance is Z0 over ZL. What does this mean? If this guy is short circuit, if you have short circuit, this is short circuit. and you move lambda over 4. What's the input impedance? Z0 over ZL. ZL is 0, short circuit. So the input impedance will be open circuit. So if the load is short circuit and you move lambda over 4, you will find open circuit here. Okay? From the equation,
Yes.
ZL is 0, short circuit. Put 0 here, the input impedance will be infinity. Of course, you have another piece of line here. But at this point, if you move the whole thing, just put open circuit. If the load is open circuit, ZL is infinity. What's the input impedance here?
Short.
Something over infinity will be
Sure.
0, so as if you have a short circuit. Remove the whole guy and put a piece of line, a piece of line. Okay? So we call it transformer. If the line is quarter wavelength, lambda over 4, it acts like a transformer. What's the meaning of transformer? It does transform short to open, open to short, from the equation. Okay? It acts as a transformer of impedance. Transformer of impedance means it will transform short to open, open to short. That's it. And it is very useful in many applications, especially in matching circuit. In matching circuits, when you try to match a device to the load, so you have a generator, a transmission line, and a load. Usually you will have reflection. To remove this reflection, you can add a piece of lambda over 4 between the main transmission line and the load. Did you get this? You will get it after you solve the next example. There's a nice example here. Look at this example. This example, we have a generator here, some generator. And that's a field line, transmission line. This transmission line has impedance of 50 ohm. This 50 ohm, this line, need to be connected to a load of 100 ohm. In this case, would we have reflection? Yani forget about this guy in the middle, as if this guy doesn't exist. Yani for the time being, forget about this. It doesn't exist. You have 50 ohm line, need to be connected with 100 ohm. Do you think we will have some reflection? How much reflection? 100 minus 50 over 100 plus 50, which is 50 over 151 over 3, I guess. Okay, this is not good. 1/3 of the energy is being reflected. To solve this issue, to remove the reflection, we add lambda over 4 line between the feeding line, between your line and the load. This lambda over 4 can remove the reflection. This addition, the transformer line, will give you 0 reflection here and 0 reflection here. Okay? So it will act like matching circuit. It does match the line, the feeding line with the load. I know it's a little bit confusing. Inshallah, when you read the example, you will understand what I'm saying. When you go and read the example. The last case, if the line has impedance equal to Z0, yani ZL equal to Z0, what is the input impedance in this case? You have some line with certain Z0, characteristic impedance, ending by a load equal to Z0. What is the input impedance at any distance? Z0, there's no reflection. The input impedance at any point is the same as Z0. Yani the load equal to the characteristic impedance. There's no reflection. This guy disappeared. Look at this equation. Look at this equation. See this equation? If ZL equal to Z0, what is the input? If ZL equal to Z0, what is the input? Z0. Completely matched transmission line. There's no reflection. Yani if the line with certain Z0, 50 ohm, ended by 50 ohm load, you have no reflection. At any point, the impedance is Z0, is 50 ohm. Okay, this is a matched transmission line. So how many cases we have covered today? How many special cases of transmission line? We have covered the short circuit transmission line, and we have got this impedance. We have covered the open circuit, and we got the other impedance. We have covered the application of open and short circuit. And if I give you these two equations, you can find Z0 and beta A, right? Also, we have covered the when the line has length of lambda over 2, half wavelength, or n lambda over 2, the input impedance will equal to, in this case, in this case, the input impedance equal to what?
ZL.
ZL, the same as ZL. Okay? And when the line is quarter wavelength, lambda over 4, the input impedance is Z0 square over ZL. And when the line is matched, the input impedance is Z0. When the line has load equal to Z0. So we have 1, 2, 3, 4, 6 special cases, which are all of them is application of this equation. And if you understand how to handle this equation, these stuff are very easy to conclude even if I don't give it to you. And you can easily find out the impedance in each case by just using this simple equation. زي ما impedance. Any question يا شباب? Before we move to the new last section, this is an application microwave oven. How does this microwave oven work? The microwave oven. How the food gets heated. We have a microwave in ID. You are using microwave, right? Who has microwave? Raise your hand. You never thought how does it thing work every time you put something? You thought about it, Abdullah?
Yes, it emits standing waves, and the evidence for that, if you put food, there's certain areas that get hot, whereas there's other areas that do not get hot. Thus, we have a rotating plate on the bottom.
You remember when we spoke about electric dipole, if you have an atom, some atom, the atom has nucleus and some electrons here, right? And then you apply electric field. Then you have an atom, nucleus, protons, and some electrons. And then you get electric field. What's going to happen to this atom? It will get polarized. Polarized means the negative charge will come here, and the nucleus will stay there. So it will be like positive in one place, negative in the other place. Get stretched. You know why? Because the electric field, assuming the electric field is generated between positive and negative polarity. And if the electric field is moving this way, this means we have positive and negative here, right? This positive will attract the electrons to this side, and the protons will stay on this side. So at the end of the day, you will have electric dipole, positive nucleus, what is Zarra, and the electrons on the other side. This motion of electrons causes vibration in the atom or the electrons. This vibration gets the molecules to get heated with the motion and the vibration. This is exactly what happens in the microwave. First, the food must contain some water, because water are very good in having electric gradient. The water has good response to some extent. Once you have electric field applied on water, the electrons will move quickly to form electric dipole. This motion of the electron will cause the food to get heated because of the motion and vibration. So we have here a microwave generator, microwave source that sends about 2.4 gigahertz signal. The signal will get reflected. We have a steerer, something to scatter or rotate the field, the electric field. Once the electric field is applied on the atoms in the chicken contains some water, so the water has good response to the electric field. The electrons start to move, and during this motion, the food will get heated. If you have food with less amount of water, it will take more time to get heated. The more water you have, the quicker it will be heated. So it's only due to the formation of the electric dipole, the motion of the electrons under the excitation of the microwave signal. We have here this relation between the penetration depth of the, once the electromagnetic field is applied on some material, it will go inside the material to a certain limit, okay? And it will not go all the way. Assume you have some material here, and you have electric field. The electric field will go inside, then it will start to decay. The penetration is based on the conductivity of the material. Based on the conductivity, you can have short or long penetration. The more conductivity, the less penetration you will have. You understand this? The more conductivity, and if the material has good conductivity, the electromagnetic wave cannot go inside. This is the reason we are in the elevator. If this room is fully metallic, you will receive no signal in your phone. Are you getting this? Do you know why? If you are in the elevator, metallic box, or in the basement, you receive no signal. Because the waves can't go in the good conductor of this metallic walls. It will die quickly. Okay? As if we have full reflection. If the whole thing here is metallic walls and the waves come on this metal, it will get reflected because metal is short circuit. Everything will be reflected. You can understand this way, or يعني there's no penetration of electromagnetic field in good conductor material. The more conductivity, the less penetration, and this behavior shows this. It's just information, it doesn't come in the exam. I will not test you with this. وقالوا الحمد لله الذي هدانا لهذا وما كنا لنهتدي هدانا الله. Now move to the last part, which is section 2.9 and section 2.5. Section 2.9 about power flow. So far we have been speaking about V and R. We have never mentioned power, right? Did you mention anything about power? Now we need to speak about the power flow over, again, lossless transmission line. We need to understand how the power flow takes place. Remember, we have two components of the voltage. We have incident voltage, incident wave, and reflected wave. Yeah, some wave is going from the generator to the load, and some wave going backward. Does the power behave the same thing? Do we have incident power and reflected power? For the voltage, V and I, we have incident voltage, which is from generator to load, and reflected for V and I. Is it the same case for power? Huh? What is the average of this? Look at this sign or cosine. What is the average value?
Integration over period.
The average is some line here. The give you the average of this magnitude. The average of all of this is some constant value, some DC value, like DC. So what is the value of this red line? The integration, as you said, from high school, it is the area under the black curve. Look at this black curve, f of x, the integration a to b over the range b minus a. This will give you this red line magnitude. Alright? You took this in physics, math 000, I guess. What's the meaning of this equation? Can anyone explain this equation to us? From where you got this equation? Yes, Abba.
The summation of the individual elements. We sum the individual elements, then divide by the number of these elements. So the integration is just go to infinity by these elements.
The summation will go to infinity.
Yes.
Some part of your answer is okay, is that this integration is area under the black line. As if you divide the area in small pieces, then you add all the division to form the total area. But still, yeah, what is the meaning of the average value here? What is the average value is this guy? Maybe they made a mistake. Look here, Shabab, this equation means that the meaning of this equation, the area under the black line is the same area under the red line. Do you see this? What is the area under the red line? This length times width, right? If average times b minus a. This area under the red line is the same area under the black line. This will make this guy's average. Are you getting this?
Yes.
Yeah, what we have here is that the area under the black line, same area under the red line. This means this area here is the same area, must be the same here. For this equation to be correct. This extra piece here must be the same. So this will make this line is the average value. Because we have the same area. The same area under this guy is the same under the black line. Does this make sense? Yeah, this is an intuition, right? Just some intuition to understand the meaning of this. Having said this, so the average value of this function, of this EC, voltage, power, whatever, some function, is this red line. I think you have been exposed to this, to the average power. Remember what is the meaning of the average power? The complex power has two components, real part and imaginary part. What's the meaning of the imaginary part and real part? 2-1. Yes, you have taken B, or it was S, I guess it was S, the complex power is B plus JQ. This is the complex power. The some real part and the imaginary part. What's the meaning of this? What is this?
Loss. The actual.
This is the power distributed in resistive load, which is the average. This is the average power. And the imaginary part is the, which is what? The power stored in inductance and capacitance, right? The average of the instantaneous power, yeah, this is the power as a complex number. If you go for the instantaneous power, B of t, the average can be found using this equation. What is the average of this?
0.
This cosine, right? 1 minus 1 will give you 0. The average line is the middle, 1 minus 1. No average. This cosine. Cosine anything is is zero average. Anything in the argument has zero average. What is the average of this?
2.
2.
The other cosine or sine.
2.
The average is, this is the same guy here shifted up by 2 volt, by 2 DC volt. So the average now is 2. What is the equation? This equation is cosine. What is the equation of this?
Sine.
2 plus cosine, the same. So looking at this equation, the average of this equation is the DC value. Forget cosine has no average, as if it doesn't exist. Cosine has no average. The average of this DC plus AC is the DC value. Okay? Here, there's no DC, it's all cosine. Regardless what is inside the argument does, can be anything here. The average is always 0. If you have a DC value, constant value, plus cosine or sine, you will have the average is this guy. The average is a real part of the complex part. Okay, Shabab, this is very important. It looks trivial, but it's very important to understand the shift in the signal is the average value. Because inshallah next time we speak about the instantaneous power flow in transmission line. Thank you, Shabab.